Okay, so here we go, a brief history of AI as we kind of know it. So we're gonna start out with the perceptron, which came out in the 1950s, and Time News magazine made this big deal about how it could separate between two different categories. People were super impressed with this machine, and essentially what happened is they built a machine, kind of as far as I believe, out of resistors. They built a machine that could when you show it two different categories and you tell it which category they belong to, like this is a this is a this is an oval or this is a rectangle, then it would take that and it would be able to determine whether or not the new inputs that it had never seen before were a rectangle or an oval or whatever. And Time magazine kind of blew it up. They're like, oh man, like is it sentient? And like there was this whole thing, which sort of ended up leading to the first AI winter. So you had the 1950s, you had the beginning of artificial intelligence, and everybody heuristic searches and all of these things, and people really excited. And then you see this major decline once people start realizing that you cannot separate, or with the current approach, you could not separate categories as long as they were not linearly separable. So then a lot of people were like, oh well, we were overhyping this whole thing and stopped kind of like looking into it. And then you have a reemergence of the interest in machine learning um, in the 1980s. So here we are in the 1980s and 1990s. Predominantly the 1990s, as far as I understand, is where a lot of the more modern neural networks that we can understand it kind of developed. So here's the two AI winters on the left, and leading into the new AI of the 2020s. And then over here on the right, I just wanted to make kind of a note that a lot of what we see in neural networks today is kind of a direct cost of extreme decrease in the amount of cost per a cost of computation. So if you look at how much it costs to compute things over time, it has gone exponentially down. And this is on a logarithmic scale. So when you have a linear line like this on a logarithmic scale, you know that it's basically halving every year as time is going on. So we're getting this extreme decrease in the computation costs. So let's go over a little bit how we saw um, how we saw artificial intelligence kind of boom in the 1990s and the early 2000s. So we're starting out with support vector machines. So support vectors is, you can think of support vector machines as kind of like breaking up one thing into multiple components. So if we think the most classical example in mathematics is in sine and cosine. If you have something that's sine and cosine, what you're doing is you're taking up a vector that might be going in both the x and y axes, and you're breaking them into separate vectors, only x and only y. And that's what sine and cosine are designed to, is to pull out these the vector component that points in a direct line. So then what you can do is you can basically take, instead of just it's in this example, you have just x component and just y component, and you look at the x and the y, and it points to a place, and this one points to a place. You can take this much further, basically saying, hey, what is a human? And you can be like, a human is built up of multiple components. And for an illustrative purposes, you could say like, oh, there's glasses, nose, eyes, ears, and then you could be like, or the color of the skin, and all of those could be components that then point to basically a unique person, but they're with different axes. So you have x, y, z, theta. Like you can have like 2,000 different components, and then when you get different values of these components, you can get these new machines. So that's a support vector machine. Very interesting stuff. Definitely look into it. And then you also, in the early 1900s, or I think this is the late 1900s, you have gradient boosting. So basically, people found that if you have one model, you could train it, and then you could have multiple different submodels basically that could then combine together to get a more effective solution. Because what you can have essentially is a local optimum for each individual model that then combined can have a better global minimum than if you're training a global minimum as a whole. And then also in the late in 1990s came out was reinforcement learning. So with the idea of as we were saying earlier here, where you're going to, in the state machine, where it's going to be either one category or another. Essentially what we're doing with reinforcement learning is taking this idea that you have this guesswork. So a new input comes in, and our goal with the reinforcement learning, or with the neural network, is to say, hey, what category does this belong to? Well, with reinforcement learning, you're saying what score am I going to get given this action and these states? So then the reinforcement learning algorithm is going to predict the score. It's going to say, I think that given this state and given this action, you will get this score. And then for every single new state that you're given, what you're going to do is you're going to give the you have the new environment. You're going to give the interpreter you're going to give the interpreter all the states and the environment, and then it'll outspit what it thinks the reward might be. And then from there, I'm sorry, this is poorly explained. So you'll give it your environment, you'll give it all of the available actions that it can take. The interpreter is then going to guess which one, or going to guess the reward for each of those actions. And then you will choose normally the highest reward, and then you will take that action, and then you'll enter into a new environment. And then there's a whole slew of things that you can do to try and increase the speed for reinforcement learning and things like that. And then so those are the predominant things that come in there in the early 2000s. But then by the 2010s, we see the advent of deep neural networks, convolutional networks, deep RL, and GAN. So deep neural networks is essentially taking what we had learned earlier with the perceptron and saying, which was instead of having one input layer, we have multiple input layers, and then before we reach the output layer. And what this ends up being akin to is a lot like a neural net, the neurological structure of the human brain in actual humans. And so we have these neurons that then fire and then activate other neurons and whole other neuron sets. So the coolest things about deep neural networks is that you can get very nonlinear decision functions coming out of deep neural networks. And so this kind of respawned a whole new understanding of what we can do with neural networks. Secondly came out was a convolutional neural network. So one of the things that was really interesting about convolutional neural networks is that they actually encode adjacent data. So one of the problems with neural networks up to before you have computer vision is that you'll have all of these inputs, but they're like, if you take all of these inputs of a pixel, if you're going along one at a time and you're getting all of these inputs, and then they're sent over to an image, it's if you take this 2 and you scale it, like move it up and to the left, and you have the exact same 2, this point here is now, instead of highlighting here, it's highlighting down here. So what you're realizing is that you don't really get the structure of the input coming out if you just put in all of the points. So what they do is they do a convolution, which is you take this square here and you get all of the inputs of that square, and those are sent into the neural network. And what this allows you to do is to pull out basically the information that is aligned next to it. So if you have this 2 that looks like this and you move it up and to the left, the convolution is going to pull out the exact same sort of information as it goes across the input. So you have a combination of deep neural networks, convolution neural networks, and then also deep RL comes out at this point as well, which is basically just taking deep neural networks and applying it to reinforcement learning. And then also we see this thing called generative adversarial networks, which allow us to create things that have never really been seen before. And essentially what you do is you give it thousands of images of, an example is you give it 1,000 images of human faces. And then you have a generator which can take noise and move it closer to something that it will take noise and it'll move it towards something that belongs in a data set. So if you have and you can think of it as something that can pass a test. So if we have a test saying, is this human or not? The generator is supposed to take noise and move that noise closer to something that would pass the test. Like, is it a human face? And then you can use a generative adversarial network to then have, and the adversarial part is to say, is this a human or is it noise? So you give it thousands of images of humans and thousands of images of just noise. And then you take what would be the noise and you say, is this noise or a human face? And the adversarial network says, oh, that's noise. I can tell. And for illustrative purposes, we can say the adversarial network looks and says, is there a nose? It takes this convolution network and says, is there a nose in this picture? And if it's no, it's probably noise, and if it is, then it's a face. So then the generator will kind of just try over and over again and realize that it is closer to answering the it's better at producing things that get by that can pass the test if it produces things with noses, quote unquote. And then the adversarial network is then trained again, and it says, oh, hey, well, now we need something else, so it has eyes. And then it'll go back and forth until we get these really realistic images that come out that aren't coming from the original data set um, because it's a member of the data set. So you have in here in the illustration, you kind of have like this overarching idea of all of the things that make up a human, and then you sample from something that's not on side of the discrete points before. So you only have a certain number of points in the quote unquote faces dimension, and then you just sample from a place that isn't one of the exact points coming in. So that's a generative adversarial network, which are really popular and have done a lot of things, especially coming into transfer. Well, okay, sorry, I'm getting ahead of myself. So then in the late 2010s, you see things like transfer learning, XAIs, and also an automation of the machine learning process. So research-wise, the late 2010s, you're coming out with so for transfer learning, essentially what this is doing is you say, hey, the information or domain transfer learning, the information that you know about this one topic. So let's say I want to sit down and play a video game. I'll be like, someone who's played a lot of video games before, even if they've never played this video game, is likely to do a lot better because they have other information from a different domain that they will then transfer into the incoming domain. So basically, transfer learning is this idea that you can get you can get a pre-trained model that is just good at video games in general, and then when you start from there and train from there, you'll quickly speed up the training process. And then XAIs is the point of XAIs is to pull out rather than just going straight from the training data to the function where like it can perform automatically where we don't know what's going on. XAIs are designed to basically train a model that explains what it's going to do and then say, these are the decisions I'm making, so that then the human can look and say, oh, I understand what you're doing, whether or not you're successful, and all of these things. And this is what I like to call like opening the black box, because a lot of neural networks today are still basically just these black boxes that you put information in, you get something out, you input to output, and there very little information is going on under. Very little information is being shared about what's going on under the hood. It's kind of just this mystery, and so XAIs are hoping to kind of like basically open the black box a little bit. And then also automated machine learning process is just like kind of a logical consecutive of what we've been working on. So basically, you have a neural net, like you have a machine, you have basically design features where you say, hey, these are the ways that we can measure success, and then you have this automation where it loops through these different processes that will then continue to make better and better neural network processes. So you kind of can step back a little bit and have the computer do a lot of the machine learning process. So now we're in the early 2020s, and we're seeing things like transformers come out. And then, so transformers, large linguistic neural networks, interest in robotics, and also wide adoption of the previously mentioned neural networks. So the thing about, so what transformers are is they're a lot like, they're kind of like they're kind of like here SVMs, where there's this idea that you break it into components, except for rather than breaking it up into components, you're breaking it up into a non-generic vector set. It's more this a more natural representation, an underlying representation. So we have this idea, this I like science coming in, and then it's going to run through an encoder. And encoders, there's a bunch of different types of encoders. One of them is SVMs, and but basically what you have is you have this underlying structure of how we represent the data, and then you put that through a decoder, and it comes out Ich mag Wissenschaft, which Wissenschaft, I don't know, something in German. And basically, this idea with the reason that we use using language here is this is something that we kind of understand, is that liking science is not exclusive to the English language, but it's this idea of enjoyment and this idea of science. And then if you as a human like science, then it's this underlying idea that most languages can represent. And we can do this with neural networks in a bunch of different ways in terms of like having these underlying representations. And essentially what they started out as is you would start with, you have a bunch of statements coming in, and then what you do is you will take the input and transfer it to a subdomain, a representer that cannot be the original input. So a lot of like it was it used a lot in like decryption. Like it's kind of like encryption and decryption, and you can take large images like this one here, and you can scale it down to like a 8 by 8, and then scale it back up to this, and you'll see that the neural networks are, and then you train the neural network to get as close to the original as you possibly can. So like let's say you say I like science, you break it up into, you get only a couple of text bits to encode this idea, and then the decoder puts out back out I like science. But then you can take the decoder and you can change it so that it fits a different parameter. So you can have encoder of the English encoders and then the German decoder, and you can translate the idea I like science into the German representative. This is what's under the hood for ChatGPT. What a lot of people are kind of getting into AI today, which has led to this wide adoption. I feel like a lot of people are predicting that AI that we are seeing released to the public today is going to very quickly be adapted to affect every part of our society as we understand it. Um, and even you have like these general pre-trained linguistic large linguistic networks um, will can affect just the mom and pop shops. Like everybody can kind of use these. You can see that for like, hey, write me an essay, do my homework for me, write me code. They're very, very useful. Also, we're seeing a large amount of interest going into robotics. A lot of people we haven't seen major amounts of money coming out of the robotic spectrum in terms of research, where you have people have been putting money into research for the last couple of decades, but we haven't started to see compounds on that investment. Basically, a lot of people like Boston Dynamics and things like that are putting out really cool products, but those products aren't directly making a difference in what people are able to pull out of them. So we're seeing that but in 2020, we're starting to see that, hey, we've kind of more or less have the ability to solve problems on the coding aspect. But if we have a problem on the physical aspect, it's not something that we can totally solve yet. So if you want a robot to go up and do your roof for you, that's just any general roof, we're not even close to that. So there's a lot more interest going into the robotics section, and then also there's a web adaptation. So in terms of the future of AI can kind of do anything, including sort of what this video probably could have been. In the next couple of years, the video that I just created now would very, very easily be done by an AI. A lot of the information that I just talked about can be talked about in AI. Like you just ask ChatGPT, give me a timeline of LTA or LSTM, and it'll tell you about the long short-term memory like networks and what they're used for and when they're used for. So if you want to know more about this, just go ask ChatGPT to give you an overview of maybe what happened in this era, and then just ask you to tell you more about the individual things you learn about. And then pretty soon we'll start to be able to use things like make a YouTube script about LTSM, and it'll do the intro, the body, and then we can take that and we can pair it with these text to video chats, and that will have now you can put full avatars that will speak in any language you want with different tones of inflection and things like that. So pretty quickly, AI will be taking over all aspects of the world. And lastly, I want to talk a little bit about this whole cost for computation. As we see the cost of computation go dramatically down, we're going to see AI take over more and more aspects of the world. One of the things, though, that's interesting to note is people have been consistently projecting that this is going to level out. We haven't seen it level out in the last couple of years, which was kind of astounding. Because up to like 2018 or so, everybody's like, yeah, of course it's going to keep doubling. But then towards the end of like 2019, everybody's like, okay, it's going to start. We're no longer going to be able to half the cost of um, because like we've been halving the size of transistors every year. And so with halving the size of transistors, we're able to basically double the amount of computation that we can get into an individual chip with the same amount of power, more or less. But the towards the end of 2019, 2020, we're starting to see that we're pushing the physical limits of these transistors, the size of these actual transistors. So we're like, okay, it's going to start, leveling out. But even with that, we started seeing that in the last couple of years, we found new innovative ways to continue to half the cost of these, of computation. So it looks like computation is going to move towards analog computation, which will give us even more computation. So as long as this trend continues, we'll continue to see AI sort of just dramatically increase, and sort of like change the way that we understand how the world works. So yeah, I don't know. That was a quick video. Let me know if there's anything else you want me to talk about, and hopefully these videos will get a lot better as I work on them.